Are the Elements Elementary? A short essay written and read by Bruce Mills, otherwise known as the Obligate Pedestrian. I have a copy of The Skeptical Chemist, part of the Everyman's Library series, that has an introduction by M. Pattison Muir, but which is undated. In my experience, if an English language book is undated, then it was published around 1930, plus or minus. Apparently, for a decade then, publishers decided not to date books. While that is bad, at least knowing this, one can approximately date an undated book. Looking up Mr. Muir on the interweb, I find one Matthew Moncrief Pattison Muir, FRSC, FCS, 1848 to 1931. A British chemist and author. He was famous for his textbooks and historical studies more than for his chemical research on bismuth, which was reportedly quite significant, but with which I have no familiarity. The Wikipedia entry for Prof. Muir states that in the long-running water controversy, 19th to early 20th century, Muir wrote one of the few British books to properly credit Lavoisier as opposed to Cavendish for proposing that water was a compound rather than an element. This, of course, is the problem with history. Everything is a can of worms. I find this interesting because in the 20th century historical works that I'm familiar with, Lavoisier is mentioned almost to the exclusion of Cavendish on this topic. The controversy is wrapped up with phlogiston, as ideas of water were essentially that water was hydrogen and oxygen, or that oxygen was water and phlogiston. The full story has more details and seems to be more about culture than about chemistry. In 1878, Muir published in the journal Nature an article entitled, "Are the Elements Elementary?" The resonance for me with this is that I see essentially this question as having been the core topic of chemistry back to the 1500s and of alchemy before it. The matter was only given a definitive answer with the advent of quantum chemistry in the 1920s. While I do not agree with Muir on his denigration of essence in alchemy and praise of element in chemistry, his situation in life, at the time when the classical theory of chemistry was all but complete and the quantum theory of chemistry was only a glint in the eye of electromagnetics, gives an invaluable insight into the development of the chemical concepts. My own position is that alchemy and chemistry are both science, and that chemistry is simply the smooth continuation of the ideas of alchemy under a 16th century neologism. If you're not happy with the assertion that alchemy is a science, then I'm quite prepared to change my position to saying that I am studying science and proto-science in the same essay. The precise definition and transition is not my concern here. I particularly eschew argument based on implicit conflict over the meaning of words. Rather, my concern is in comprehending the rational process of both alchemy and chemistry and focusing on comparison rather than on contrast, to unify the notion of the historical studies of studies in materials. In this process, one can usefully explicitly study the impact of different meanings of words. Where things go wrong is where either semantics takes over the discussion or competing views each claim the others are wrong due to implicit differences in the semantics of the language, so that the actual difference of technical fact are not really being discussed, but rather it is a cultural fight over the pragmatics of the language. Muir begins his article with, "It would be curious speculation were one to ask oneself what is the atomic weight of ozone. Is it 24? Is its atomic formula O1.5? Or has oxygen the atomic weight of 32 and ozone of 48? And are the molecular weights 64 and 96 respectively? This can scarcely be, for the smallest amount of oxygen in 2 volumes of a gaseous compound of that element is certainly not 32 but 16 parts per weight. In fact, atoms of allotropes scarcely appear to exist. The molecule appears to be the smallest amount of one of these substances that can exist either in or out of combination. But can elements really exist in combination under various allotropic forms? We do not know. Weber thinks they can, Clark thinks they cannot. The example of graphitic acid, sometimes cited as proof of the existence in the combined form of allotropic carbon, does not appear to me to prove either one view or the other. Graphite, may we not say, is an intermediate stage in the formation of graphitic acid from carbon? but it does not follow that the carbon in the acid is in a form different from that under which it exists in, say, sugar. But it is exceedingly difficult as yet to attach a definite meaning to such a statement as carbon exists under different forms in this and that compound. End of quote. I always find it fascinating when an historian becomes history. Here is Muir speculating on the nature of the conjectured atoms and molecules. In 1878, the existence of atoms in a physical sense was considered conjectural. The stationary and complex atom of the chemist was in conflict with the dynamic and simple atom of the physicist. Each theory worked in its own scope, but it was hard to reconcile them. This is the situation with relativity and quantum in the late 20th and early 21st centuries. The existence of atoms as a physical thing rather than a mathematical abstraction is often considered to have been first established by Einstein in his 1905 paper on Brownian motion. Related to this is Becchelia in 1900, supervised by Poincaré, who worked out the mathematics of the Brownian motion process. It was first described by Robert Brown in 1827. Muir also seems to be saying that even though we are convinced that carbon exists in sugar and in graphite, we do not know whether it is the same form of carbon or even if that distinction has any meaning. In terms of quantum chemistry, it could be pointed out that the electron orbitals in sugar and in graphite are not identical, and if the atom is the nucleus and the electrons, then in a sense it is not the same kind of atom but a different kind of atom. Determining that they are both forms of the element carbon is a matter of determining what the meaning of the word element is, where its boundaries are. How far can an atom of carbon be modified and still be carbon? Is carbon radioactive? Some isotopes of it are. So if all those isotopes are the same element, that element cannot be said to be radioactive or not. A sample of it might or might not be. In this meaning, an element does not always have definite properties. Why should isotopes of carbon be considered the same element? They have different masses, they have different nuclear configurations, and nuclear configurations take a lot of energy to switch between. Why not call them different elements? The practical reason is that the meaning of the word element in chemical terms has evolved to be distinguishable by a conventional identified collection of measurements known as chemical tests. This excludes measurements of the mass, even though measurement of mass is used as an element identification. The atomic theory definition of element is the number of protons, but that does not go without saying. It was a choice, ultimately based on the chemical test definition. There is much convention and pragmatics in the meaning of the word element. An allotrope, in its 21st century definition, is one of the many forms in which an element can exist while in the same state, where state means essentially being solid, liquid, gas or plasma. This is a curious thought, as elements are intended to be elementary, that is, fundamental. How can they have different forms? The answer is usually, at least implicitly, in terms of the geometry or the arrangement of fundamental parts. Like a mill pond or a rainstorm are different forms of water at a macroscopic level, although they're the same thermodynamic form, liquid. Also, if the element carbon can have different forms, then there is nothing illogical about the idea proposed by Thales that water, taken as a fundamental material, should have the ability to take on different forms and yet still be the same fundamental material. Clearly, lead and gold, which are not considered allotropes, behave differently, but they are more similar in many ways than diamond and graphite that are considered allotropes. The idea of allotropy was young when Muir wrote the article. It is attributed to John Jacob Berzelius, who is generally famous in his own right, but he is not the topic right now. Once Avogadro's hypothesis was accepted in 1860, it became possible to consider the idea of allotropes of oxygen in the gaseous state. In particular, Avogadro's hypothesis, made in 1812, is that at a given temperature and pressure, a given volume of any gas contains the same number of particles. This is a very strong practical hypothesis. It is not self-evidently true, and in fact it is strictly false. Deviations from Avogadro's hypothesis, where the same number of particles takes up less volume, are just called supercompressibility. The rule is a rule except where it is not. But the principle can be derived from mathematical argument using the assumption that the particles are tiny and do not interact. However, with this idea in mind, it then became a shock to find that the same mass of what seems to be oxygen can exist with two different volumes, one being half again as big as the other. Does that mean that what is identified as oxygen is really two elements? Perhaps ones that are chemically related? In effect, the question is, are oxygen and ozone two different elements or different forms of the same element? Much of this discussion again becomes a matter of semantics. Exactly what is the word element to mean? The working principle is something like that which is never created or destroyed, and that means that neither oxygen gas nor ozone gas are elements, since they can be created and destroyed using laboratory techniques. But rather there must be an element, which we can call oxygen element, such that the oxygen gas is composed of a kind of double dose of this oxygen element and ozone of a triple dose. Then the common oxygen gas would be more rightly called dioxygen, and ozone would be trioxygen or oxygen 3. In the journal Nature, November 13th, 1927, Bachowski and Copeland published an article, An Active Form of Oxygen. It stated, an active form of oxygen, presumably monatomic, has been produced by passing oxygen gas saturated water vapour through a discharge tube. The gas was generated electrolytically and subjected to a discharge of about 1000 volts at gas pressure of 0.4 millimeters of mercury. End of quote. The low pressure prevents the oxygen atoms from coming into contact often enough to form dioxygen gas. Monoxygen is very reactive. Ozone itself was first made in the laboratory by Christian Friedrich Schonborn in 1840. Schonborn was interested in discovering the source of the odour produced by electrical discharge. The idea that chemistry and electricity were related had come from the work of Volta on the battery, published in 1799, and Humphrey Davy in the production in 1827 of potassium using an electric arc. In each case, it is interesting to note that the monoxygen and trioxygen were both generated from the more common dioxygen using electricity. The issue here is that it was determined that dioxygen and trioxygen were not elements due to being able to break them apart by electrical rather than chemical process to create monoxygen, which in turn failed to break apart. If something can be broken apart by electricity but not chemical means, does this mean that it is automatically not an element? In principle, it might have turned out that monoxygen could be broken apart as well, if enough energy were supplied, and in fact this is exactly what was discovered later in terms of nuclear reactions. If the electricity is in the form of electromagnetism is strong enough, then it rips the atom apart to make protons and electrons. The neutrons are rather unstable, in effect establishing oxygen to be a compound of smaller elements. The idea of the so-called ancient elements of earth, water, air and fire is often juxtaposed with the elements of hydrogen, lithium, etc., of classical, circa 1900, chemistry. But given that the medieval alchemists such as Pseudo-Geber in Summa Perfectionis, circa 1305, thought of the classical metals, mercury, copper, iron, zinc, gold, silver, lead and tin, as not being fundamental but rather being super tightly bound combinations of earth, water, air and fire, this is much more analogous to a lead atom being composed of protons, neutrons, electrons and photons. The better analogy to the classical elements in terms of modern chemistry is that earth, water, air and fire are protons, neutrons, electrons and photons, pragmatically fundamental particles in the realm of chemistry. True, the theory of Pseudo-Geber was nowhere near as sophisticated or empirically successful as quantum chemistry, but it is recognizable as broadly the same concept. In the same article, Are the Elements Elementary?, Muir continues, the positive evidence in favour of the theory of non-elementary nature of the so-called elements is not very great, yet to say that the elements are truly elementary is, I am persuaded, a statement which is not justified by the facts which we possess. Either hypothesis may be adapted as working hypothesis. The former, that the elements are not elementary, is, it seems to me, likely to lead to more discoveries and to pave the way to more far-reaching generalizations than the latter. But why should no one have succeeded in decomposing one of the so-called elements? In a sense, we have succeeded. Ozone is an element, but it can be decomposed. Oxygen may, I think, be said to be the simpler form of matter than ozone. End of quote. It is particularly of note that Muir states that ozone is an element. This presumably was the norm at the time and was due to the fact that ozone was not created at the time by chemical means but by electrical. The conflict between Lavoisier and Priestley over whether water was an element was of similar nature. The idea that an element such as oxygen might not be elementary after all is prescient in that in 1897, after the article by Muir, Thomson showed that cathode rays were composed of small electrically negative particles. He described this as knocking a bit off an atom, and this was shocking because the working hypothesis was that atoms were fundamental. Thomson also found the first evidence for the existence of stable isotopes. The idea of a monstrous form of an element, a grotesque of a different weight, can be more readily accepted if that form is unstable and returns to one of the known elements in weight. But it becomes more problematic when it exists in a form that would seem as elementary as the one originally discovered by chemical means. It would have initially been assumed that the weight of the element was characteristic and not contingent. Returning to the matter of electrical decomposition of materials, in a sense, helium is a compound of deuterium, an isotope of hydrogen. Two deuterium atoms can make a di-deuterium, the molecule, or helium, the supposed element. They both have 2 protons, 2 neutrons, and 2 electrons. The distinction is in the precise configuration. In di-deuterium, the 2 protons are further apart and less tightly bound, but they are still there, just as they are in helium. Certainly in modern terms, a nuclear reaction is involved, but in comparing this to the studies of the alchemists in general, they were simply interested in how materials could be transformed into each other. The idea of a nuclear reaction is still a reaction. It has reactants and products. Limitation of the alchemical research as being by definition a badly formed idea of chemistry and not nuclear physics is anachronistic. Pseudo-Geber in the 14th century did not consider there to be a strong boundary. In particular, he recognized the principle that some materials were strongly bound combinations of the prime materials and that others were loosely bound combinations of these strongly bound combinations, which is a statement of the same idea as nuclear physics versus chemistry. But this was all in the scope of alchemy. What makes helium an atom and di-deuterium a molecule is a matter of convention regarding the amount of energy involved. If one does not have at one's disposal the techniques of quantum chemistry in which the theory does provide a clear and identifiable distinction. But that was not to be until the mid-20th century. It was as yet unknown in the 19th century. The modern distinction made between alchemical elements earth, water, air and plasma and the essences, properties, of hot, cold, wet and dry is artificial when it is declared that the latter is not considered to be materials. The principle is that each element has 2 essences. Earth is cold and dry, water is cold and wet, air is hot and wet, and plasma is hot and dry. This can be taken as a choice of basis of a vector space. That is, it can be said that north-west is a combination of the directions north and west, or that north is a combination of northwest and northeast. Each is a valid way of looking at the relation. Now there is a technicality here in that 1 unit north plus 1 unit west is about 1.5 units northwest, by Pythagoras. This suggests an asymmetry. In terms of elements and essences, the same problem arises, but this can be made entirely symmetric by using scaled combinations. If one combines by the process of adding the directions and then scaling to unit length, the making northwest from north and west is complemented by the making of north from northwest and northeast. The rather gratuitous rescaling is precisely that which is used in quantum mechanics combination of states, which are taken as being on the surface of an abstract unit ball rather than being a vector space. The thrust of this entire discussion has been around the point that for the past close to 3 millennia, people who studied the behaviour of materials have been trying to comprehend the reactions in which materials are created or destroyed or perhaps transformed in terms of underlying prime materials that are eternal, the superficial changes being only the result of changes in combinatorics. There has been an ongoing discussion and gradual evolution of the choice of which materials to consider to be prime, and there is some ambiguity in this, in particular before the advent of Avogadro's rule, which enables the number of particles of a material to be counted, at least up to an unknown scaling factor that is independent of the material. In particular, before the late 19th century, measurements of the number of particles were not available, and this led to ambiguities in the declaration of materials as elementary, a particular case being that of what is called atmospheric oxygen gas, elemental oxygen gas, and ozone. Ozone was accepted as an element for a while, and the relation was determined only when it started to be possible to count atoms. Quantum mechanics, atomic physics, has cut through this, enabling the derivation of the list of elements. But this only occurred in the mid-20th century. Before that, from the 1600 to 1900, the chemists were working with the same basic problem that alchemists were from 1100 to 1500. In this sense, quantum mechanics is the culmination of 2,500 years of thinking about the nature of materials.